day, students. How are you? Welcome to our science class. This is your teacher, Ma'am Zenaida M. Cruz, and I hope you are excited to learn something today. So, what are you waiting for? Let's learn science.
Do you know Efren Bata Reyes? Have you watched him play? And did you wonder how he plays magic during his games? How he controls the billiard balls? Some of his tricks can be explained in physics. In our topic, conservation of momentum. And for our objectives, explain the total momentum before and after collision is equal. And solve simple problems on conservation of momentum. Let's recall some of the important words that we have discussed in our last discussion. I have here scrambled letters for you to guess. I will give you a picture and a definition as your clue. And this is our first word. This is the picture that may give you a clue. And for its definition, it is the sudden, forceful coming together in direct contact of two bodies. What word is this? Very good. This is collision. This is the second word. This is our clue. And this is our definition. So bodies collide and move away from each other. What word is this again? This is elastic. Very good. Next word. This is our picture clue. And it is defined as it occurs when two objects collide and do not bounce away from each other. This type of collision is inelastic. Very good. The words that you have guessed a while ago are the types of collision. How can we identify whether they are elastic or inelastic? After the object collide with each other, did they stuck together? If your answer is yes, then the collision is said to be inelastic. But then, if your answer is no, then the collision is said to be elastic. Let's watch and look at this Newton's cradle. What can you say? What observation can you get from this? You got it right. When the first marble on the right collided with the second, the energy is transferred to the third, to the fourth, and lastly, to the fifth marble. That movement will also be the same if two marbles will hit the third, the fourth, and the fifth will also move and vice versa. The movement of the marbles in Newton's cradle can be explained by our lesson for today, which is the conservation of momentum, which states that the total momentum before a collision is equal to the total momentum after the collision if no external forces act on the system. And speaking of a closed system, In a closed system or isolated system, the total momentum of the objects before and after collision are equal, and it can be explained mathematically by this equation. The mass and velocity of an object plus the mass and velocity of another object before collision is also equal to the mass and velocity of both objects after collision. Let's explain this conservation of momentum by this sample problem. Two billiard balls has a mass of 0.1 kilogram each, or equivalent to 100 grams. The cue ball has an initial velocity of 6 meters per second when it hits the fifth ball. After the collision, the cue ball stopped and the fifth ball moves. What is the total momentum of the system? And what is the velocity of the fifth ball after collision? Let us identify the given data in the problem. So we have here the mass of the cue ball, which is 0.1 kilogram, with its initial velocity of 6 meters per second. And the mass of the second ball, which is 0.1 kilogram also, with an initial velocity of 0 meter per second because it is at rest. We have here our formula, which says m1v1 plus m2v2 is also equal to m1v1 plus m2v2. Then, remember that the total momentum before collision is equal to the momentum of the first ball plus the momentum of the second ball. In symbol form, the total momentum before collision is P1 plus P2, or momentum 1 plus momentum 2. Since momentum is equal to mass times velocity, then the equation above becomes momentum before is equal to mass plus multiplied by its velocity. So substituting the values, so we have here 0.1 kilogram multiplied by 6 meters per second plus we have 0.1 kilogram multiplied by 0. So what we have here now is zero point 0.6 kilogram meter per second. This is the momentum of the two balls before collision. After solving for the momentum of the balls before collision, can we now solve for the velocity of the second ball after collision? Yes, we can. With this formula, the momentum of the first ball after collision is equal to m1 v1. And the formula for the second ball after collision, we also have m2 vis of 2. So after collision, the total momentum is equal to the momentum of the first ball plus the momentum of the second ball. Take note also that in this case, ball 1 stopped, while ball 2 is the one that moved. So, computing for it, we have the total momentum after collision is equal to the piece of 1 plus piece of 2, or momentum 1 plus momentum 2. The momentum after collision is equal to 0 plus 0.1 kilogram multiplied by the v sub 2. Momentum 1 here is 0 because, as we said a while ago, ball 1 stopped. Then, the momentum after, or the total momentum after, is now equal to 0.1 kilogram multiplied by the v sub 2. Since the momentum before collision is equal to the momentum after collision, which is according to the principle of conservation of momentum, then 0.6 kilogram meter per second is equal to 0.1 kilogram multiplied by the v sub 2 after collision. Then, to solve for the v sub 2, transpose v sub 2 at the left side of the equation. This gives us v sub 2 is equal to 0.6 kilogram meter per second divided by 0.1 kilogram, and cancel kilograms and kilograms in here. So we will have a final answer of our v sub 2 after collision, which is 6 meters per second. For our v sub 2 after collision, we can now prove that the total momentum before collision and after are the same with our formula m1v1 before collision plus m2v2 before collision is also equal to m1v1 after collision plus m2v2 after collision. So, substituting that, though we have already computed for the total momentum before, we still have here 0.6 kilogram meter per second plus 0 because ball number 2 is at rest. And then after collision, M1V1 is 0 because the first ball stopped plus 0.1 kilogram multiplied by 6 meter per second, which is the velocity of the second ball after collision. So from that, we come up with this answer there. So the momentum before, which is 0.6 kilogram meter per second, is also equal to the momentum after collision, which is also 0.6 kilogram meter per second. And this explains our law of conservation of momentum. In our example, the system is isolated because we consider only the interaction of the two balls. We did not consider the interaction between the ball and the table. We study here only isolated systems to make the situation simple. However, in college, when you will be in college, systems to be studied may no longer be isolated, and that makes it more exciting. And this is our conservation of momentum. So, from our lesson on conservation of momentum, we have proven that the total momentum before a collision is equal to the total momentum after the collision if no external forces act on the system. Mathematically, it is expressed with this equation. The principle of conservation of momentum doesn't apply only to collisions. Look at this first picture. When the skaters stand facing each other, both skaters in here have zero momentum. It's because they are not moving. So the total momentum of both skaters is 0. In this letter B picture, when the skaters here push away from each other, the momentum is equal but opposite. So the total momentum is still 0 because they are in different directions. Let's go back to Newton's cradle. We have here 5 marbles of same mass. The first marble from the left was pulled and released. One marble from the right moves. Then, if we are going to pull two marbles, how many marbles from the right do you think will move? Very good. It will be two marbles. Same as the number of marbles that is pulled and released from the left. And this explains our lesson on the conservation of momentum. Look at this bowling pin and the bowling ball. What happens when the bowling ball hits the pins? If there is no forces applied, the total momentum of the bowling ball is transferred to the pins and the pins go flying. So all the pins carries all the momentum. So the momentum that the pins gained is equal to the total momentum the bowling ball had it before it hit the pins. Momentum is not lost or created, only transferred. That is conservation of momentum. Another application for conservation of momentum is a rocket launched. Rocket gains momentum in the up direction, and on the other hand, the hot gases gain momentum in the downward direction. Just like our example a while ago when two skaters pushes each other. Get a sheet of paper and let's answer this question, which says a 12,000 kilogram railroad car A is traveling at 2 meters per second when it strikes another 12,000 kilogram railroad car B that is at rest. If the cars lock together, what is the final speed of the two railroad cars? So we have here the given, the mass and velocity of railroad car A, which is 12,000 kilogram and a velocity of 2 meters per second. And for railroad car B, we have a mass of 12,000 kilogram and zero velocity because it is at rest. So this is our formula. So we have the mass and velocity before collision plus the mass and velocity of the second railroad car before collision is equal to the mass and velocity after collision of railroad car A plus the mass and velocity after collision of railroad car B. So the mass and velocity of railroad car A is 12,000 kilogram with a velocity of 2 meter per second. And the momentum of car B is 0. It's because it is at rest. And after collision and the two cars stuck together, they will now move as one. So their masses will be added. So we have m1 plus m2 multiplied by our vis of 2. Then 12,000 kilogram multiplied by 2 meters per second plus 0, we have 24,000 kilogram meter per second, which is also equal to 12,000 kilogram plus 12,000 kilogram. We come up with 24,000 kilograms multiplied by the vis of 2 after collision. So putting vis of 2 at the left side of the equation, we'll have 24,000 kilogram meter per second divided by 24,000 kilograms, and we cancel kilograms together. So we have a final answer of v sub 2 after collision, which is equal to 1 meter per second. Again, this v sub 2 is the velocity of the two railroad cars that are stuck together after collision. Let us check our answer if the momentum before and after collision are the same. This is our equation. M1V1 before collision of the first railroad car plus M2V2 before collision of railroad car B is also equal to M1V1 after collision of railroad car A plus M2V2 after collision of railroad car B. Substituting their formula, we have 12,000 kilograms multiplied by 2 meters per second plus 12,000 kilogram multiplied by 0 because railroad car B is at rest before collision and equals 12,000 kilogram multiplied by 1 meter per second. This was the velocity of the two cars that we have computed a while ago after collision plus 12,000 kilograms multiplied by 1 meter per second. So we now have here 24,000 kilogram meter per second. This is the total momentum of the two cars before collision, and this is also equal to 12,000 kilogram meter per second plus 12,000 kilogram meter per second. So now we have 24,000 kilogram meter per second. Again, this is the total momentum of the two cars before collision. And we also have 24,000 kilogram meter per second, the total momentum of the two cars after collision. So we can see in here that the total momentum before and after collisions are the same. In here, we have proven that the total momentum before and after are the same, and that is the law of conservation of momentum. I hope you enjoyed learning with me.
That's all for now, students. Again, this is Mom Zenaida M. Cruz, your science teacher, saying, be good, do good, feel good. Good day and keep safe always. Goodbye.